So I wanted to just have a look at the inverse sine function. The first thing I wanted to do was to recap our exact values, and we'll do a bit of a speed run just to wrap our head around the exact values. These two triangles here can help us determine our exact values. All you need to know is that sine of theta is equal to opposite over hypotenuse. So sine of 30 degrees is going to be 1, that's the opposite side to 30 degrees, over 2. So that's 1/2. Sine of 0 degrees is 0. Sine of 45 degrees is 1 over root 2. Sine of pi on 3, well, now we're standing at 60 degrees, that's pi on 3, is going to be root 3 on 2. Sine of pi on 2, that's equal to 1. Think about your unit circle there. Sine of pi is 0, 3 pi on 2. We're down on our unit circle down the bottom, so we're at -1. And then this is at 0 again. Now you can see on our sine graph here, all those points match up. All along here, that matches up nicely. So for example, pi on 2 corresponds with the sine x value of 1. Okay, so what we want to start to do now is we want to start to build some intuition for our inverse sine function. Now the first thing we need to be aware of is that not all functions have inverses. In order for a function to have an inverse, a original function must be a one-to-one function. Now, our original sine graph is not a one-to-one function. Now, there's two criteria for a one-to-one. One-to-one function must pass horizontal and vertical line tests. So what it means to pass a horizontal or vertical line test is that if you draw a line horizontally or vertically, it only touches the graph once. So for example, at the moment, if I draw a horizontal line on y equals sine x, that's clearly not one-to-one because it does not pass the horizontal line test. Okay, at the moment it actually does pass the vertical line test, but it needs to pass both. So what we need to do is we need to restrict the domain. And conventionally what we do is we restrict the domain between negative pi on 2 and pi on 2. Now you can see just in this interval, ignoring all this now, or ignoring all that other stuff, in that interval that I've shown here, this part here, if I was to draw a horizontal line in that interval, there's nowhere I can draw it that's going to hit the line twice. Similarly with the vertical line, there's nowhere I can draw that vertical line that's going to hit that part of the graph more than once. So that's conventionally how we restrict our domain, and so maybe we can write that. So our sine x domain equals negative pi on 2 to pi on 2. Okay, and the range equals -1 to 1. Okay, and that's important. So we're just considering that little portion of the graph there, because the next thing we're going to do is we're going to start to think about what the inverse function will look like. Now, what we have over here is actually the original graph. So it's just that section that I highlighted. This is just y equals sine x. Okay, so what we want to do now is actually want to think about what the sine inverse looks like. And you might recall that the inverse function of anything is just a reflection in the line y equals x, which is why I've drawn this line here. So let's just label this blue line, this blue dashed line is the line y equals x. And so we need to reflect the red line in that line. So it can be a bit confusing, but basically all the x and y coordinates swap. So if this coordinate is at negative pi on 2, -1, then this coordinate down here, roughly, will be at -1. So it needs to move a bit further to the left. It's going to be at -1, negative pi on 2. So it's going to be, I don't know, there somewhere. Okay, and try it yourself or take my word for it. It's going to look something like that. And what we can say is we know, hopefully, so it looks roughly something like that. It's not perfect, but we can say as well that the domain of sine inverse of x, remember when you find the inverse of a function, the domain and range swap. So the domain, and we can even see it here, is going to be from -1 inclusive to 1 inclusive. And the range of what we call sine inverse of x is the domain of the original, which is -pi on 2 to pi on 2 inclusive. So hopefully that clarifies what the sine inverse graph looks like, and hopefully you get a bit of a feel for why the sine inverse graph looks the way it does.